This is the first video for this section looking at pollutants and the important properties of pollutants that help us figure out where are they going to go, where will they wind up. Will they be in the atmosphere, in the lithosphere, which we most usually think of as soil, in the biosphere, that is in living plants or animals, or in the water, the hydrosphere. So these are a bunch of properties you probably already know quite a bit about. This is just a little bit of review to get us all back on the same page. So the properties that we're going to talk about here, first I'm going to give you a little bit of a reminder about equilibrium. We'll talk a little bit more about equilibrium chemistry a little bit later on. But the other sort of major properties of chemicals are water solubility, the partitioning coefficient, which you may not have heard of before. This one is the octanol water partitioning coefficient, vapor pressure, Henry's law constant, and persistence. And in this video, we're going to focus on equilibrium and water solubility, in order to keep it short. Okay, so first we're going to talk just a little bit of a reminder about equilibrium and what that means. So when a system is at equilibrium, all concentrations in a solution or in the system, they're all constant, and there's no change in concentration levels or in energy. The same thing is true for a chemical system. If you have products on the left side and reactants on the, oops, I said that backwards, products on the right side and reactants on the left-hand side, all those concentrations are constant once you get to equilibrium. None of them are changing. And there's no change in energy. You're sort of at the lowest energy state that you can be at for that system. So the reactions may be going on. C and D may be turning into A and B and vice versa, but the forward rate of the reaction, that is A and B turning into C and D, equals the backward rate, that is C and D turning into A and B. So again, this just means that all the concentrations in this chemical system are constant. So equilibrium really tells us about the expected final state of a system. So after it's been sitting there for a long enough time, nothing's changing anymore, what does that system look like? Okay, so then moving on to water solubility. You're probably fairly familiar with this. This is just a bit of a reminder. So a general definition as a property, water solubility is the ability of a given substance, usually called the solute, to dissolve in water. Pretty straightforward. It can also be thought of as the maximum amount of a substance or solute that will dissolve in water at a given temperature and pressure. So this is an equilibrium property. After you mix something up with a bunch of water, how much of it will be in water, how much will not be in the water. Okay, so here's a little bit of an example. You say you have 5,000 grams of table sugar or sucrose, and you throw it in 1 liter of water. And you stir it up a bunch. You're at 25 degrees Celsius. You let it sit there. You stir it up. Everything that's going to dissolve dissolves. Only 2,000 grams of that sucrose is going to dissolve in water. No matter how much you stir it, 3,000 grams are just going to be sitting there in the water. So this means that the solubility of sucrose at 25 degrees Celsius is 2,000 grams per liter. Hopefully I've been saying 1,000 and not 100. 2,000 grams will dissolve. 3,000 grams will be sitting there. Okay, so polarity and water solubility. So this is kind of getting back towards maybe a little bit more of your chemistry, and this is what will help us figure out what different pollutants are going to do. We can predict, are they going to dissolve in water, or are they going to form a different layer, or just sit there as a solid? So water is a polar molecule. I'm sure you're familiar with this idea. You've got 2 lone pairs of electrons sitting on top of the oxygen. So that gives this part of the oxygen molecule, or the water molecule, a negative charge. And then you've got these 2 hydrogens sort of pushed down to the bottom, so you've got a net positive charge down here on the bottom. So, reaching back into your chemistry, do you predict that polar or nonpolar substances would have a higher water solubility? So you can think about that for a moment. And you've probably aren't going to pause it, but we can move ahead and see that probably sounds familiar. Like dissolves like. So polar solutes, polar substances, dissolve in polar solvents, that is water. And nonpolar solvents dissolve in nonpolar solutes dissolve in nonpolar solvents. So you can think of this as something like acetone or nail polish remover. So if you have something that, for example, water won't clean off, it won't dissolve in water, like nail polish, you can use a nonpolar solvent, like nail polish remover, to get that to dissolve off of your finger. And this is just a cartoon that I thought was sort of amusing, but that just means that I'm a little bit of a geek. Whoops. Okay. So here is just an example. This is a glucose molecule, and it shows you how it interacts. It's a polar molecule, and it shows you how it interacts with the water. So we've got the sort of negative portions of the water molecules interacting with the positive portions of the glucose molecule. And charged ions, as you probably know, will also dissolve in a polar solvent. So that's just a salt. So you've got the positive, in this case, this is sodium chloride. So you've got the positive sodium ions surrounded by the negative portions of the water molecule, and the negative chlorine ions surrounded by the positive portions of the water molecule. So you can see it dissolves nicely in water. And this is just giving you some examples. So at the top, we've got a nonpolar substance, naphthalene. It's just carbon and hydrogen. And you can see it's got a really low solubility in water. A polar substance like urea has you can see it's polar, so you'd have your lone pairs of electrons up here creating some negative charge and some positive charge down here. Dissolves really well in water, really about 1,000,000 milligrams per liter. Sodium chloride, this is just to sort of give you a frame of reference, doesn't dissolve quite as well in water as urea, but still very well. Okay, and then you are probably used to thinking about this, solids and liquids. For both of those things, solubility increases with temperature. And anybody who's ever tried to dissolve sugar into a glass of iced coffee knows this, especially if you like sugar in your coffee like I do. It's a lot easier to dissolve sugar in a hot cup of coffee than it is in your iced coffee. So this is a little contrary to maybe what we want to think of gases as doing, or things that dissolve in water as doing. But for gases, solubility decreases with temperature, and this becomes important when we talk about climate change, which we will do in class. So this is just a figure showing you solubility in water with temperature, and you can see, especially for carbon dioxide, this decreases pretty rapidly as temperatures increase. So less and less carbon dioxide dissolves in water as temperatures increase. The same is true for oxygen, but you can see that slope is a lot lower. Okay, so the next video we're going to talk about the partitioning coefficient, the octanol water partitioning coefficient.